Okay, hello class. Module 3, text mining, image compression, or data compression. So let's start by sharing the screen. Let's go to your class. Okay, so in module 3, so it says text mining, but we'll cover some other things too. Could be image or compression. 3 things we've gotten here, some software that we're going to use in MATLAB. So you can, you'll see in the assignment some links, but this is also, they're also copied here, some of the files. So some text files that you'll see in a demo that I'm going to give. And the tool is called TMG for Term Matrix Generator, and some slides for a tutorial that I'm going to go through during this talk. Lots of reading material. This is a little 4-page extract from one of my favorite books by my postdoc mentor at NC State, Carl Meyer. So 4 pages there, just a short little thing about how the singular value decomposition of a matrix helps with information retrieval. This is a PDF file of a website. The link is in the assignment. It's better to look at it as the website, but I did download and extract the PDF. This is maybe a, I don't know, 10 or 15 page article that I wrote actually when I was about your guys' position. So it was a couple years into graduate school and got into search engines. I wrote this article. It appeared in JAMA's online math module. And then these are slides that you'll see in today's talk. So I put those there. And then lastly, the assignment. So let's take a look at that. Okay, so again, we'll be doing some text, mostly text mining, but we could also apply these ideas to images. So if that's something that you want to work on this week with your team, and information retrieval. Again, some of those things are mentioned here. You can also just follow the links when you open the PDF file. Tutorials, again, the things that are in OAKS are also on my website. Talk, a couple of their books that are referenced. One that I love in information retrieval, it's a short little thin, maybe 90-page, small little 5x8. Mike Berry is at the University of Tennessee, Knoxville in computer science there. A wonderful book, and he's got a couple small thin ones and websites that have to do with this. Was the one that really got me into text mining. Tim Chartier is a nice applications of linear algebra book that has a couple chapters that might be useful for you. So you should be able to find that at the CFC library. This is another really nice book, Lars Eldon over in Europe for data mining and pattern recognition. Really well written. And if you have linear algebra, you can understand everything in that. Okay, and then what you're going to be doing this week is finding a data set of interest to you. Again, that's the key thing. What's something that you guys are interested in? We've had folks that did presidential candidate speeches in the past. People have looked at movie data. So Netflix, a lot of these things are available. You can check them out. Just Googling, but there's a website like Kaggle or InfoChips. A colleague of mine is now at Purdue, David Gleick, loves to collect data. You might go to his website. Or you could scrape your own, and there's plenty of tools for doing that. Maddox has done that in the past. He has some really nice data sets that he's worked out and collected. And there are tools in MATLAB to help you scrape your own data too, for if you want to get things off the API on Twitter, or I think that's already a built-in function. Okay, so you're going to use this tool, TMG. I'm going to give you a demo of that. Once you've got your data set, so you're going to create a term by document matrix, a feature by movie matrix associated with it. Again, we'll have a demo and instructions. You can get the file here, or it's also in the books. You'll do a little exploratory data set, get to know your data, any interesting things that you find there. Then you're going to pose questions, right? We want an interesting question. A good question is start you off on a quest. So things that you're interested with this data, why did you collect it? Why is it of interest to you? What are some of the things you can do? And at least 2 of those questions are going to involve finding similar vectors. We'll get to that in today's lecture. And we can do it with the vector space model, something called the latent semantic LSI model, or the non-negative matrix factorization. And then you're going to pose some more questions at the end and give your presentation. Okay, so usual format there. Okay, so then let's next go to talk about these topics. So we'll start with this talk I gave a long time ago, again with my, let me get the screen size right here. Okay, this one I gave a long time ago with my co-author and mentor, Colin Meyer at NC State. So we're going to talk about traditional information retrieval, and I don't know that I'll get into too much of the web information retrieval. We did a little bit of that last week with Markov chains and PageRank, which, by the way, Brin and Page didn't even realize when they were first doing stuff with Markov chains with PageRank that it was a Markov chain. They were actually thinking of it from a summation computer science. You're important if other important pages point into you, and that was a summation that they were solving. Okay. So focusing on what is called traditional information retrieval, this is not searching on the web. This would be a static collection or one that's changing over time, but every so often you take a look at it. So you're looking at this static A matrix. So like you can think about the Addlestone collection at CFC as a static one, your local public library, curated certain collections that are in a museum. And we're going to talk about these models here from the 1960s and 70s, the vector space model, then the latent semantic indexing was in the 90s, other vector space models, and then in 2000, there was this major one, the non-negative matrix factorization that really came along and had a lot of applications. Okay, Gerard Salton was the guy who invented this system called SMART for people, sometimes called Salton's magical automatic retrieval of text, but it was mechanical analysis and retrieval of text, so his SMART system. And what he would do is he would take text documents, so like the students that work with the presidential campaign speeches, each speech, that was when they were looking at Trump and Clinton, so they had, say, 10 speeches by Trump and 20 speeches by Clinton, and a total of 30 speeches. Each speech they considered its own document vector, so a vector row or column, however you want to think about it. Let's maybe think of them as columns here. We'd put all of those in a matrix A, which is an M by N matrix. And we'll talk about how you build that. You're not going to obviously do this by hand. We're going to use software to help us do it. And then we want to use that matrix to retrieve information. So we'll create a query vector that looks a whole lot like a document vector. And it's actually called a pseudo document. So we'll have some examples in the next couple of slides. And our goal might be to find the document vector that's closest to the query vector. So like which speech from Trump is closest to a speech by Clinton, or you have a particular topic. In fact, I think the students, I'm trying to remember this, maybe there was some claims that Trump's language was sort of fascist. So they made a query vector from like other fascist leaders, like Mussolini or something, his speech, and then they tried to find which Trump's or the average of Trump's, the distance between Trump's to Mussolini and the distance between Clinton's and Mussolini. So we can think of those lots of ways of finding the closest one, but we're going to use the angular cosine measure, which is really just a vector or an inner product, a dot product that you learned in your calculus or linear algebra classes, normalized by the length of those. So really, we're just getting a vector inner product ON measure calculation. Okay, so that book that I mentioned before, Mike Berry at the University of Tennessee, Knoxville, wonderful book. This example comes from that. So let's suppose that we have these 7 documents, which are just really the titles of books. So we can be as drill down as much as we want. Here we're just at a high level. Maybe again, we're doing a curated collection in a museum. We just look at the titles of the items in the museum's collection. Same thing here, we just have titles of documents. Now, but our dictionary of terms is only these 9 things. So that means if a word like first aid isn't in your dictionary, it's like it doesn't exist. So really the yellow words are the only words that we're really getting. So when we're classifying and collecting this information for document 1, we're just saying, okay, it used infant once, it used toddler once. So that was term 6 is going to have a non-zero value in that vector, and toddler is the 9th term. So that'll have a 1 there. You can count how many times they have weighted collections. So we can create, there's our matrix A, it's terms, term 1 through 9 by documents 1 through 7. So we have a 9 by 7 matrix. And as I said, document 1 is this column, it used term 6 once and term 9 once. So this one ends up binary, but often again, you could just have counts here. A query vector, suppose the query vector we wanted to find information on terms 1 and 4, which in this case is baby health. So we would find the angle between Q and each DI. And here's the angle, the cosine angle measure, delta here. And it's saying that it's actually closest to, this is a 7-dimensional vector because it's the number of documents you have, and it's saying that document 4 is actually closest to the query for baby health. That makes sense. It actually has it right there in the title. Then it's saying 5 is next, baby proofing, and then this one's interesting. Beanie Baby Collector's Guide. Really, if we had used all the terms, that wouldn't be useful, but because it's just baby guide, it's saying that one's a good match, right? And that's a limitation of our dictionary over here. Some things you do with vector space models, you measure things called precision and recall. Precision is the number of relevant documents retrieved over the total number of documents retrieved. So if we're talking about like Google on their first page, they show you 10 things. So that's the denominator. If 3 of those were actually relevant to the query, you get a score of 3 out of 10. Obviously, the higher the better. And recall is if in the entire collection there were 7 relevant documents and I only returned 3, I get a score of 3.7. Okay, some things that we can note is that you could normalize the columns of A and Q, and that'll speed your cosine calculation because, right, we don't need to calculate those denominators, that everything has been normalized to have length 1. So we don't need to do this calculation. We're just doing the O end here. Oh yeah, so there, one vector matrix multiplication at query time. Some things you have to decide is what is your cutoff for what makes a document appear as relevant and it's displayed to the user. Is it 0.7, is it 0.8? That's a lot of engineering and tuning for the particular system. You can weight the elements in A. Again, in this example, they were just counts, which ended up in this case just being binary, but you can weight those. There's lots of ways of doing that. And some of the software we'll look at, you want to research these ones as you read about them. This one is very common, the TF-IDF, term frequency, inverse document frequency. We'll talk a little bit about that later. Many ways, lots of research has been done on that. You can also do things like stemming and stop listing, and we'll talk about that. In fact, we're going to use that text to matrix generator, TMG tool. Okay, so what's good about this vector space? This is an early model. It was revolutionary in the 60s and 70s. We were using computational power to do a much better job than the card catalogs. So the matrix is sparse. We can do these vector matrix multiplications really fast. They can be done in parallel. Here's a neat one with relevance feedback. If you look at the results returned, so again, kind of in a system like Google, 10 things show up on the page in a GUI. For your local library, let's say, 10 things show up. You can then say which of those documents were most relevant. You can give weights. And you can say, I actually liked, of the 10 things you showed me, this one, document 1, 3, and 7 were most important. And then it'll take that and make a revised query, Q tilde, and send that back, given that information from the user. So it's like feedback loop. Okay, but there's some downsides. It has decent performance, but when there's noise in A, we'll talk about that. Particularly, you might think about this, like if our data is, let's say, an audio signal, maybe there's background noise, and that noise affects your A matrix, but you can maybe denoise it somehow, and we'll get to that with the singular value decomposition. Noise in terms of text mining might be things like synonyms and polysems. So maybe if we denoise the A matrix, we're taking words like car, automobile, vehicle, and pushing them into one pseudoterm or megaterm or something, right? This is also assuming with the vector space model, really what's underlying it, the underlying basis vectors, which are the standard basis vectors. E1 stands for 1, 0, 0, 0. E2 stands for the vector 0, 1, 0. So in three-dimensional space, it was the axes, right? I, J, and K. Well, those axes in three-dimensional space and in n-dimensional space are orthogonal, which really is saying that your terms are independent. But is that the case? Right? In any language, it's probably not the case. So it's a bit of weakness. Plenty of resources. Again, I'm going to point you to, and what is in the OAKS is that short article on JAMA, a couple of other examples in that one. And Mike Berry's website has plenty of other data sets. It's maybe a bit older. He hasn't done as much research on that lately. Okay, then came along in the 1990s, the latent semantic indexing. This was Susan Demey's improvement to the vector space model. She was working at Microsoft, still has and is one of the world's leading information retrieval researchers. Well, this idea that she had was she was going to use a low rank approximation to the A matrix, and that would filter out noise. And we'll talk about what that means. We'll see it visually with some examples. This got a couple patents. Interesting to read if you're into that sort of thing. I am. Okay, so what she was doing was using the SVD. And so this is a decomposition that you probably learned about, or if you haven't, it's similar to in linear algebra, you learned some decompositions like you certainly learned Gaussian elimination, which is a LU decomposition. So it takes a matrix A, and it says that is the product of a lower triangular matrix and an upper triangular matrix. It can always be, there is such a LU decomposition for a matrix A. And so you can ask in MATLAB, input an A, and ask for the LU decomposition. It'll spit out two matrices, U, L, and U, with certain properties. And there are many different decompositions, and they all have different properties. Well, the singular value decomposition has the property that it will take a matrix A. Every matrix A has this SVD that will be decomposed into three matrices, U, sigma, and V. These three matrices, when they're multiplied together, give you U back. I'm sorry, A back. If A is a rank R matrix, then you can also think about this decomposition as a bunch of outer products. So these are a column vector times a row vector makes a rank 1 matrix. We talked about those last semester. Remember the rank 1 update, the Sherman-Woodbury update. So we have a rank 1 update that is weighted by this sigma. So sigma is a diagonal matrix. So it only has entries along the diagonal. So sigma I. So sigma 1 is the most important, most heavily weighted of the rank 1 matrices that make up A. And then you add the next most important one, sigma 2. It's also got a rank 1 matrix associated. So A can be split into three matrices that are multiplied together, or it can be thought of as a sum of rank 1 matrices. And so Susan's idea was, well, every matrix has that. And it goes up to R. Instead of going up to R, let's take K, where K is much less than R. So we're really just getting the K most important components that make up the matrix A. And this is called a low rank decomposition. It's a wonderful idea in general for lots of applications, but we're going to use it for information retrieval. And it often, she found it improved performance. So on query processing or clustering. Okay, so what's really happening here is that there's a change in basis. Instead of using the standard basis that we talked about before, I, J, K, right? So in three-dimensional space, those are orthogonal. It's really going to shift those, and we'll be taking the singular vectors associated with matrix U. So that U is made up of a bunch of column vectors, and really we're just weighting them. So it's saying a particular document vector, say the first column of A corresponds to document 1. It is really made up of vectors in U, weighted by the sigma, so how important it is, and elements in that corresponding V row vector. And again, we would still use the angular cosine measure to measure how close documents are to a given query Q. However, this time the document vectors now are going to be replaced with their A sub K approximation. Instead of A times E1, we're doing A sub K times E1. Right, so it looks pretty similar, but we're just using this SVD decomposition in place of A. because we're doing a low rank approximation. Okay, some properties of the singular value decomposition is that the vectors in U are orthogonal, but the U and V are mixed in sign. So even if A is non-negative, which it often is in text mining, right? We showed that example from Mike Berry's book. Those were non-negative entries there, and the counts of the number of times a term appeared in a document. And yet U and V could be mixed in sign. Sigma is certainly non-negative, so that does carry that property in the diagonal matrix sigma, but we could have some negatives. Again, we'll look at some examples in a moment. A downside is that U and V are typically dense. So even if your matrix A started sparse, which it probably will, think back to the Berry example, lots of ones and zeros, lots of zeros in there, was a sparse matrix, you're trading that sparsity for the density. Even though there are fewer vectors, K is much less than N, but they're going to be dense. You do have the advantage of uniqueness. While there are many SVD algorithms that produce an SVD, they all create the same truncated factorization. Another nice property is the optimality of all rank K approximations that you could come up with, and there's lots of different ones to do this, whole field research into low rank approximations to a matrix. This is the optimal one in the Frobenius norm. Okay, so again, for folks in our 451, 551, you remember optimization problems, we're trying to minimize something here. Okay, so here is the, let's take, for example, this matrix, which is the A matrix from the example before. It's a 9x7 term by document matrix from Berry's book. It's been normalized, so the columns have length 1. But here's the rank 4 approximation, and you can see it's kind of getting there, like this is a 0 and this is a negative 0.00 something, right? This is a 0 and it's a negative 0.7. So, but it's pretty off here. That's a 0.2 and it should be a 0. Here's the 0.63 and it should be a 0.7. So, it, you know, it's getting there, right? And again, you see here's sparse, dense, 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 right? So that was the downside. But A5 is getting a little better. A6 is better still. Right, it's getting closer. It's using more and more information though. So you'd like to figure out what is the K? Should I use 4, 5, or 6 or 7? Well, actually the rank of this rank has rank, this matrix A has rank 7. So that's as far as we can go. And you see that the rank 7 actually recovers the actual matrix back as it should, right? If we use all the data. And the trick is, what is the K that has this compromise between being close enough to this, but yet denoising. And that's, again, an engineering problem. These links are actually old. This talk is so old. Okay, strengths and weaknesses. Again, if we do this, Susan found this, many other researchers come along. Yes, it improves performance, which is your precision recall, and plenty of other measures too. You do this dimension reduction, you're only considering the essential components of your matrix, so you're filtering out noise, and is the best rank K approximation. However, again, the vectors in U and V, these, for whatever your approximation K, are probably going to be dense. It's harder to interpret the basis vectors because you can have negative signs, and it's like, what does it mean to be negative in the negative direction for the term health, but the positive direction for the term toddler, right? Again, determining K, that's not necessarily easy. A lot of times they'll graph the distance between A and AK as K increases, and you're just trying to find where, like, it's sort of K is giving a lot of information and it's not adding much more the further I go out. Right? Okay, lots of resources. Mike Berry has a lot of papers, and again, I love this little book here by Siam 1999. We're going to again talk about this article of JAMA that I wrote. Lots of other decompositions. Maybe one you learned about, you might have learned the QR. Other things are used to do this instead of just the singular value decomposition. Okay, but maybe we'll quickly now talk about the non-negative matrix factorization because there is some code in the TMD software tool for this. Okay, so these two guys, I think, were at, I think, MIT around 2000, maybe finishing their degrees or just done or postdocs or something. And they said, instead of using the singular value decomposition, which we talked about, U sigma V, you start with a non-negative matrix, but yet you're going to use some mixed in signs and things that are negative and positive in U and V. And that seemed a little strange to them. They said it'd be nice to keep the structure. And so they, instead of coming up with 3 matrices, they decided to decompose with just 2 matrices, W and H, that they forced to be non-negative. And so a similar decomposition, but we're going to have W will be non-negative, H will be non-negative. So we have this idea of like a linear convex combination. So any column, any document can be approximated with this linear combination of basis vectors that are also non-negative. Now, it has this interpretability, and you can also make W and H sparse. That was super cool. I spent a lot of time researching, creating my own algorithms for the NMF that had sparsity. Okay, so it's about as good in terms of precision and recall, query processing, or document clustering, but you can interpret the factors. So let's take a look at that. So here's a data set that I worked with from Mike Berry's website. It's the Medline, so it's abstracts from medical papers that people in that community, the doctors and staff use. And in this case, we did a low rank approximation with the NMF. So we just used the 10 most significant basis vectors. And so we had a basis vector W1, W2, W5, W6, and we looked at the highest weighted terms in that vector. And again, there are no negative terms. There's a 0 or positive. So the ones that had the highest weight, here's the weight down here, ventricula was the one for this particular basis vector. And then the next most highly weighted was aortic, and they just dropped off, right? So I'm only plotting the 10 most important, the heavily weighted terms in basis vector W1. Well, it's easy to see just at a glance right away that basis vector is about hearts. This one here has a lot of blood flow, oxygen stuff. This is children and autism, it seems, and lots of kidney things in this one. So it's easy for a user of this to come along and say, oh, okay, so you did a low rank approximation, and now I know that of all, my whole collection has a big cluster of documents that have to do with heart things and autism, right? So you could then have an at a glance view of what your document collection is about. This is only possible because we have forced the W to be non-negative. If we were using the SVD, again, what would it mean to say that you were like -2 correlated with a term? Okay, so we were able to go in and do things like this. Document 5 in that collection, that Medline data collection, was actually built from these were the most important heavily weighted, so 0.16. So most of the weight went to basis vector W9, and the highest weighted terms there were fatty glucose acids, insulin. Then a little bit of weight, 0.01, given to this kidney one basis vector, and then a little bit to pituitary growth hormone stuff, so less weighted. So you could actually reconstruct document 5's topics and what it was about using this interpretability. Okay, again, there's sparse implementation, so it was better than LSI in terms of storage. There's some algorithms for it. Again, this was their original one. There's lots of other ones since. I've added several that add sparsity. Okay, so some more resources. Let's stop that. And now let's go. Next thing I want to go over is how we're going to do these things. Again, several times I've mentioned this tool, TNG. So I'm going to tell you a little bit how to get it. We'll do a bit of a demo here. Okay, so this is built from, if you can go to this link, or again, if you go to the assignment, there's a link there. It's also in your OAKS, how to get the tool. Probably better, instead of going to this link, use the one that's in OAKS. So let's go back for a second. one here, you want to get the 6.0, this version, right? So either this link from my website or that's also in the Oaks. Let's see, Oaks under module 3, right there, right? Back to the other tutorial. Okay, so you go get that. You've already gotten MATLAB from last week, and just some tips on where to put it, adding it to your path. Okay, and then you want to run it. So you're going to run this command at the MATLAB window, command window, initialize TMG. So, and then you're going to type TMG GUI, and this box is going to open up. So let's do that. So many windows to manage. Actually, I should just share. And just share. So here's MATLAB. Okay, I changed folder to where I had put that. Maybe I should just clear this. All right, so I had to go make sure I was in the directory that I put TMG in. So make sure you did, once you've downloaded it, make sure you switch to that in MATLAB in that same directory. And just to make sure. Okay, so I did an ls list the files there, and that does have all these GUI TMG M files. And so these are the things that come in that package. And we're going to run this initial TMG. And close these things out first. Yep. All right, so you're about to install this. Okay. Yes, database toolbox. It's adding some directories, and then the next thing it told us to do in the tutorial was TMG GUI. That. And that's open up the box display window. Okay, so here we go. Open this up so you can see it a little bit better. And what you're going to do now is create a term document matrix. So that's the first thing we're going to start with. Lots of things that we can play with here, and we're going to do the basics. What I have on your assignment, in a place you can download from my website, but also in Oaks, is this thing, haccomplishments.box. This is a text file. So let's open that. And if you want to look at that, let's actually do that for a moment. Oops. So over here. Okay, this is showing an editor, MATLAB, but it's a text file you could open up any kind of editor. This was a project that a student was working on. It was a professor at the College of Charleston that was interested in analyzing people's speech. It actually had them answer a couple questions that were just like a couple sentences or a paragraph. They were given a prompt. The survey respondents would type something in, and they wanted to analyze from their written language how humble a person was. So it was called the Humility Project. They had grants for this, but they needed help, computational help and quantitative help. And so one of the students was Tyler Perry. He's now gotten his PhD in OR, is at Rice, and teaching there. But while he was an undergrad at CUC, he did this project. So each line, so he has an end line, an empty line. Each one of these is from one of the respondents. So my senior year of high school, I completed a senior project. My project was navigated course, blah, blah, blah. My greatest accomplishment had to be getting the bridges. I was doing so. I think the question was, what's your greatest accomplishment? So, and then this like third document, D3, is just the answer getting accepted into college, right? So Each one of those is a document. It's separated by an line. And he had, I'm trying to remember, it'll tell us, if we do this right, it'll tell us. So that is the file haccomplishments.txt. So we're going to use that as one of our examples when we create a matrix here, if all goes well. So again, the delimiter is empty line. There's other choices here. Stop list, we haven't talked about that. Stop list is a list of terms that you don't want in your dictionary. So for some reason, maybe you don't want to study certain things. Often people to put in this, like there are standard stop lists you can go get. I think Tyler included one with it. So let's see if we have one. Oh yeah, stop list. He had lots of different ones, but here's one stop list. He didn't, for some reason, want some of these small words, right? Like every else. They often will stop list, general stop list that you look off the internet will often remove like these little tiny pronoun, the, and, or, but sometimes you're interested in those. He didn't want those, but I think he might have also asked at some point, maybe collected speeches from people that were considered more humble, like Mother Teresa, Chief Joseph, and so they use those terms a lot, and he wanted to just not have them in there, so stop listing them. So you can add your own, and again, there's some that are already built. So that's what it was asking. Lots of different ways of weighting. Again, read up on these, just do a Google search, Wikipedia about what they mean. Term frequency is the number of times the term is used, so usually want that. Global weighting, inverse document frequency, again, a common one. So if it appeared often in that particular document, you want to maybe downweight it. That's an inverse document. Okay, so some other things you can normalize your vectors. That's making them have all the same length one. You can stem words, which means there are tons of algorithms that will, and they have some built in here that will, we actually saw that in the berry example, babies apostrophe, all those were stemmed to the root BAB, and that's a stem. So you can take words that really are the same thing, but just different endings of it. So you might want to do that. Maybe you want to remove alphanumerics, maybe they're important to you. If you're doing things with tweets, maybe you don't want to do that. Maybe they mean something you don't want, or maybe you only want to find hashtag things, right? Or maybe you want to remove all those. So think about stop lists and these various possibilities. Okay, and then you hit continue and done. It says it's made a matrix for you. So then we go back over here, and in your workspace, you'll see that it's created some things. It's created a dictionary. So take a look at that. This dictionary is all the words that it pulled out that weren't in your stop list. So it found how many times almost appeared in each document, how many times, so lots and lots of things, right? Over 1,100 different unique words in this small collection of 100, and here we can see, this is terms. So 1,189 terms and 177 documents. So they got responses from 177 survey respondents. And that's how many separate documents you have. So 177 documents. Lots of different things to check out here. Again, you can double click on those. How many words are in each document? Remember that third one? We had getting into college, so we had 4 terms in there. Yeah. Okay, so let's do that. Some other facts that it shows in the back here. Like again, it parsed document 174, there were 45 terms, 175 had 34 terms, and so on. 177 documents, that's terms. Average term per document number. Okay, so very sparse though, that's pretty cool. It gives that. Quickly did it. Some more stuff to look at. And now that you have that thing saved, where you could enter a query, you can make your own query vector, which is 177 terms by 1, and put non-zeros where the things you're interested in, and then go find which documents, which are 177 documents, are closest to whatever your query was. Right? So you can enter that and then do your cosine measure So you can do the calculations of that. But you can also, let's go back to the top. Okay, so we're running here, creating a return document matrix. Stop this, we don't have the rating. All the things that I created there. Okay, and then we've already talked about, we got the space bar and the system match stuff. Tyler gave an example. Again, these are actually, if in his small example, there are only 3 terms. So you have 3 documents in 3-dimensional space. He's plotted them all there just to show you visually what's happening. This has a little bit more about what's happening for weighting. Usually there's a local weight and a global weight, and then possibly a document memorization. So that's how you create the entries. Local weight, again, is usually just a frequency count from the time that word occur. You could make it binary, logarithmic, so that like if it has hundreds, maybe you really take that 100 and log it, so you slash it down. And then the global weight, again, is usually the most common one. It's the inverse document frequency. And here's the formula for that. By diminishing the value of words that appear in too many documents, we can focus on the ones that are more unique. Again, if we're looking at the Medline collection, we'd expect a lot of medical terms. If we're looking, there's one in Mike Berry's website, the Cranfield collection, which has to do with like airplane and aeronautical stuff. So you're going to see a lot of words, plane, airplane, all those terms are going to appear in many, many documents. They really don't help distinguish it. And that's why you do the inverse document frequency. Normalizing, usually just dividing by its length. So that way, and this picture, just because this one's longer, maybe it doesn't matter. It's usually the angle that matters. All these vectors pointing in space, and then a query comes in. So vectors in space, a query comes in. It's important not how long they are, but the angle between them. It has to do with how close they are to each other. Yes, and our query is a pseudo document. There's our cosine angle. So this is easy to compute in MATLAB, right? You can just do that computation once you've created your Q. Now we're going to talk about this example. Okay, dimension reduction. Now, this is when your matrix right now is the full rank. So we could go back and ask, what is the rank of A? And that's what let's see. There is a sparse version of that. And they're not full with that. Let's hold that thought, but I'm pretty sure that the rank of this is going to be 177, very near that. We want to choose a K that's much less than 10, 20, 30, I don't know, it depends on what you're trying to achieve with your particular data set. But here's a visualization of what's actually happening. Here is what's happening when you're compressing your data by doing truncated SVD. When you're truncating, instead of taking the full rank R, you're doing something less, possibly much less. So A of K, then we're just taking the first K column vectors of U rather than all of them. We're taking just the first K diagonal entries along this diagonal matrix rather than all of them. And same thing, just the first K vectors, which in this case V transpose would be row vectors, and we're using that to build A sub K. Okay, we already talked about precision and recall, but usually dimension reduction for a language has a lot of noise, synonyms, misspellings, polysyllables, and it's going to improve performance. But dimensionality reduction could also be thought of if we're doing images. So you can read in images. You can take a picture of your phone, read it into MATLAB. So I'm going to show you how I did this. I just had an image. And then I did a couple grayscalings or blue scalings, I think, on this one. And then I tried to create the, well, I did create the truncated SVD. So I asked for the entire SVDS, which is for sparse. That was the command I was looking for earlier, SVDS. Because A is sparse, and I'm only going to use, these are my, so just do a help on SVDS in MATLAB. And this is the documentation, or you can do it up here in the search documentation over there. So here's the example of the usage, right? So U, S, and V, I decided to do this with just K. That's what I'm saying here. I'm just doing this with, I called my matrix A gray, A G for gray. I wanted just the first 10 vectors. I did the SVDS, and I just labeled these U10, confirm U, S, and V, U10, S10, V10. Then I multiplied them back together to get the rank 10 approximation, and I looked at what that looked like. As you increase K, the number of singular vectors, you expect the image quality to improve, but it's going to take more storage. So rather than storing a completely dense matrix with every pixel having a value, oh, I guess I should describe that. Okay, so here's an example. This is my dog Chiche, and she's a Mexican hairless, so hairless breed. This actually, I feel like this was a little, it looks like a little doggy porn, inappropriate, but that's just a post she likes to do. Normally she's clothed this time of year. So Chiche is a little 10-pound dog, and I had this picture of her, so I just threw it into MATLAB. Again, every pixel in this makes a matrix. Like, what is the RGB value? What is the weight? So I grayscaled it so I wouldn't have to have 3 matrices with different RGBs. I just had a grayscale, and that's what I was trying to do here. And so there's a number, like in the 1-1 entry, there's a number. I think it's between 0 and 255 that represents how dark that pixel is, right? The next one, the 1-2 pixel, and so on to dense. But, and this is the original, this is the scaled RGB gray scaled one. Turns out this weird blue. And then I did my SVD approximation. So this thing is dense, right? Storing that takes a lot of data. But maybe if I can compress that using the SVD, I only needed 10 vectors, 10 in U and 10 in V, so 20 vectors. Maybe they're dense, but right, that's better than the total number of vectors to do this entire thing. But it doesn't look much like Chiche, right? But I did 50 vectors, and maybe you see a little bit there's her face and her ears. 100 vectors, it's getting a little bit closer, right? So that's a lot better than storing the entire, I forget how big that image was when I did it, but it was a lot bigger, right? So a lot of savings in storage. That's how you can do SVD for image compression. Okay, now other things are possible in the TMG tool. Lots of things, some of the things we just talked about with non-negative matrix factorization, retrieving documents, clustering documents, dimensionality reduction, all using the GUI command. So we'll go back into TMG. We say GUI. Okay, here's this box that just opened up. And we can click on these different things. So maybe we want to reduce the matrix, okay, that we've saved. We want to do a single value decomposition. That's the one we learned about, but we've mentioned these other ones. Research them if you're going to use them. Don't just point and click. Right, but we'll stick with SVD. And we have to say some things like number of factors that we want. That was in the image compression, I was doing 10. Put any number that you want there. Oh yeah, we have to enter a data set. We'll use the humility one again. Okay, it says it's done. Let me go back to our workspace and we see what's happened. Oh, it has created a U, a V, and an S. That's the sigma. So those are the 3 matrices. And notice that the original matrix A, in this case, 1100 by 177, U is that many terms by just 10 columns, because those are the compressed, right? And then this is just a 10 by 10 matrix. If you looked at SVD, it's just a diagonal matrix, right? And those are the weights, always non-negative. They'll put them in order. So that's saying the one that corresponds with U1 is the most heavily weighted, and then they sort of drop off. And then V is the number of documents by number of compression, the K. So you can try different ones, different K values, and let's see. That's another screen. So many screens. Yeah, so you could change that here. Let's see what happens if we do. Oops. So it updated here, and let's just see, just out of curiosity, what the SSVD matrix looks like. I just wanted to see if it started to tail off yet. No, it's still got a lot of weight. Probably if you looked at 100, you'd see a drop off in that exponential curve that we're seeing when we plot the singular values of a matrix. And that's what you're looking at, where you still have a good bit of weight, and then it should just tail off to 0. And you don't want those ones that are contributing nothing, right? Just more work and more storage that you don't need. All right, then let's play around. This slide is showing there's other things you can do. We had just done. We did dimension reduction, but maybe you want to do retrieval. Data set again. A query, I'm not sure that you can just enter terms, but let's try it. Do you use a stop list, target rating, vector space model, or LSI, or latency random indexing with single value decomposition? You could do that, or you could just do a basic vector space. Cosine measure, let's stick with that, that's all we've learned. Number most relevant, let's see what happens. Interesting, we didn't use them. Okay, I'll give you stop list. I do have them. I don't know how to get this query, and that seems to be the issue here. So we'll have to play around with that to figure out how to enter a query. That's the problem. It's giving some results, but it didn't have a query. The query is empty, it's saying. So I don't know if you have to give it a vector, like actually write it as a vector. But let's see award. Let's see if that one will work. Let me try that term. Maybe the word emission wasn't actually in the dictionary, so it didn't make sense. So then it's showing some information here. It's saying that document 50 has a similarity, cosine similarity score of 0.4. I'm not sure what this means with data. I think it just doesn't know how to retrieve that. But let's look back here also in the command window and see what they have to say. So there was only one query that we had, which was on the award. Find me all documents closest to the that have to do with award. See how many times people in the humility data set mentioned that their greatest accomplishment had to do with an award. Okay, so this is just normalizing that query and making it a pseudo document, basically. That's what that is. And then it found that one. I'm not sure. There seems like there should be more, but you could play around and check with that. Let's then do go back to the one more. One more thing. Let's try the clustering. Let's say maybe this is again what the students tried looking at clusters with the presidential campaigns this year. Like Hillary was mostly talking about international topics or something, or Trump is always on oil, let's say. they could try to see if that worked. So we have our data set. Lots of ways of clustering k-means, probably some of you are familiar with that. That's in CS or data science classes. PDP is actually using the SVD underneath of it, so it's really neat. SVD can also, besides compressing data, besides denoising data, besides being used to do information retrieval and query processing, can be used to cluster. So you can say how many clusters do you want? 5. Again, don't really just do the defaults if you don't really know what's going on. Oh, sorry, number of clusters. I think that's what they want. Okay, so it's saying that, oh, it did find this, that cluster 1 had a lot of accomplishment stuff in it inside, but then cluster 2 also, graduating, a lot of college stuff. I guess the prompt was my greatest accomplishment. A lot started by answering that. So it looks like cluster 2, definitely, you can see maybe that makes some sense. So it has to do with how many clusters you've asked for. Degrees, master's degrees, college stuff. Oh yeah, lots of high school graduation things. Interesting. So anyway, you can check that out for whatever your data set is, whatever you're trying to do. I'm not sure though why it's giving it so many clusters. I think it has to do with the number of how I do this. Because I worked as a consultant for SAS in their text mining group, and they had software that used the SVD. And at the time we were telling them, hey, there's this new thing called the NMF that has all this interpretability that's great. And we did sell them on it. They actually loved it. They converted a lot of their software. There's a proc NMF and SAS that we helped them build. Oh, and the proc NMF in MATLAB is actually cites work with Mike Berry and me from one of our papers. And so at the SAS Statistical Software Text Mining Group, we then went back to their SVD and started looking at it. And we were able to figure out the SVD could help you cluster. And how it's doing that, it's if you asked for k = 5, it can cluster by looking at sign changes in the U and V. And because U and V can be positive and negative, you could have 2 to the 5. So 32 different possible clusters. So that's why when we hit 5 principal directions, it's really finding at most sign patterns up to 2 to the 5, which is 32 different, right? 32 different. So there could be that many different clusters. So it's just looking for these sign patterns. That's a whole nother talk. I love it. It's really interesting, but I don't want to worry way into this one. 58 minutes into this one. Okay, so let's go back though to the talk, see what else in these slides. Oh yeah, there's some clustering. We already talked about NMF. Oh yeah, so if you need help on these things, we've talked about this before, documentation in MATLAB last semester. You can just pull that up and do a search. Like if I wanted to know what's going on with the NMF, here comes up the help page. Here's a proc that's already built in. Here's the WNH that Lee and Sung are doing. All these bells and whistles, and it shows you how to use them, gives example usage. Oh yeah, so then this is a nice slide. Your term by document matrix, you will say how big you want your K to be again, so maybe just 10 vectors. So W will have 10 column vectors, H will have 10 row vectors, and you are approximating it. That's really good approximation of the quality by topics. Then you're really taking your term by document matrix and turning it into a W, which is a term by topic. Remember those clusters that we saw with NMF, with the Medline data set. There were those ones about heart, there was ones about autism. So each one of those was a topic. So if I had 10 column vectors, we have 10 topics that are being extracted. I can look at what those topics are by looking at the heavily weighted terms in this, because again, non-negative. So I go sort each column by its weights, and then I'll pull off the most important terms. And then same thing, you would then be getting a topic by document matrix H. It's very useful to look at that interpretability. Okay, so if you want to do things with image, a good reference is which I believe is at the CFC, or it's worth having your own copy. It's a nice little small book by my colleague Tim Chartier at Davidson and Michael's Linear, lots of applications. Computer graphics he talks about. He talks about if you had an image, like I had that image of Chiche was A, and then I had, used to have a dog who died a couple years ago, Zuchi, and I wanted to know, one's a miniature Mexican house, one was a standard 75 pounder. If I want to know, one was a boy, one was a girl, if they had babies, they did. You want to do that, but if they did, what they might look like. So you could take, a lot of people do this with like, they just got married, their picture, their partners, what their babies might look like, or they want to know what, I don't know, J-Lo and Brad Pitt's baby would look like, right? So you could do some combination, you can do a convex combination, want it to be 80% Chiche, 20% Zuchi, there's a couple dogs, right? So you could blend. So he talks about that, neat applications. Another one in, I think it's in Tim's book, is also in the Lars Eldon book that I referenced at the beginning of this talk. You could, there's a data set that has to do with handwritten digits that come to the USPS. So the US Postal Service has a problem where they need to sort mail by the zip codes, and everybody has their own handwriting different. And it's hard to see. So they have this scanner that will scan the zip codes that are handwritten and then try to classify each one. So 29439 Bradley Beach is, when I write it, does that look the same as when my husband John writes it? He's left-handed, I'm right-handed, we're quite different. But you can look at those and compare them to all the other nines. You've seen 29439. So if there's 9 in there twice, let's look at those 9s. To all the other 9s that are input to the system that have been categorized definitely as 9s. And so you're trying to take an input query of my 9 and see if it looks like the average of all the other 9s that you've seen. Totally able to do that when you think about each one of these as an image. It's a matrix. Mine comes in, is it closest to this average, which is the 0, or is it the 1? Is it, or does it look like the 9? So, and how many times do I get it right? And if I get it, if I'm not sure, I can have a confidence measure associated with these. Right, so that's a cool data set. And that's in, I think it's in the large, definitely in the large ads, and possibly in Tim's book. MATLAB actually is a text analytics tool. I just Google on all these things. If you want to do a word cloud, they did this with, I think, oh yeah, President Trump's tweets, weather reports. You can do sentiment analysis, like you can look at a 1 year students collected during the Super Bowl every tweet, and then they did some things like sentiment analysis, and they decided could they divide them into Broncos fans. That was years ago, so it's like when the Broncos, who were they playing? I forget. Anyway, they were wondering if they could take the tweets and reconstruct that to make sort of a Reuters article about the game. So I wouldn't need to send a reporter there. I could just sort of crowdsource an article about what's happening during the game based on these tweets. Some really neat findings on that. I forgot about that one. So lots of stuff is already built in. I just showed you this one TMG one-off package, but there's plenty of stuff that you don't even need to do with TMG. Take a look, search this week. Yeah, positive and negative words, you can split those. I think this was straight off MATLAB's website. Okay, that's it for that talk, and I think that's it for the demo. I'm sure that anything else I wanted to say. Okay, I think yeah, pick something that is interesting to you this week, and this one's probably going to extend over several weeks. So take a look at that, and I ask you to just sort of find your data, get familiar with it, and sort of ease you into it this week, and then we'll hopefully have questions that you want, that are a quest, and that you're going to want to continue. All right, have fun.